we're going to start taking a look at sine graphs, okay, which is basically a graphic representation of all the ratios of your sine, okay, of sine on your Cartesian plane from 0 to 360 degrees, okay? So what do we know about sine? We know sine is the ratio of your opposite side over your hypotenuse side, all right? And if we were to take any particular angle around that from 0 to 360, we would be able to find a ratio for sine by taking the opposite over the hypotenuse from whatever angle that we want, okay? Now what I've done is I've given us a diagram of the Cartesian plane, and I've specified only a couple of angles, and I'm sure you'll notice that the ones that I've highlighted are all the special angles, okay? The reason being is obviously we know those values. We don't have to rely on the calculator to give us those ratios, so they're easy to work out. Okay, so what have I given you here? We've got the first quadrant in which I've isolated, or I've shown the angles of 30 degrees, 45 degrees, 60 degrees, and then up to 90 degrees, okay? And what I've done is I've written next to it each of the ratios of sine for each of those angles. So sine of 30 degrees was a half, sine of 45 degrees was root 2 over 2, and so on and so on, okay? Do you notice that in quadrant 1, which is from 0 to 90 degrees, all of those ratios for sine are positive, okay? Do you notice that? All of these ratios here are positive. Now, that confirms what we know from the cast diagram, that everything in quadrant 1 is positive, okay? Now, let's flip over to quadrant 2. Remember, quadrant 2 represents angles that are going from 90 degrees to 180 degrees. So, from 90 degrees, if I added 30 degrees, I get to 120. Added 45 degrees, we get to 135. Then if I add another 15 degrees, we're getting to 150. And then another 30 degrees, we're getting to 180. What I just did with those angles is I simply reflected what we had in the first quadrant over the y-axis, and I then found the angles in the second quadrant, okay? Do you notice, look at the left-hand side and the right-hand side of that y-axis in quadrant 1 and quadrant 2. Do you notice at sine of 30, we had positive a half? And if I reflect over the y-axis, sine of 150 was also positive a half. That's 0.71, or root 2 over 2 at sine 45, and at sine 135, it's also 0.71, or root 2 over 2, and the same can be said for those angles over there. So they're exactly the same. The reflection about the y-axis was identical on the left and the right-hand side, okay? Remember, the ratio for sine is your y over your r, okay? If you're reflecting a point about your y-axis, do you agree with me? It's your x coordinate that's going to change sine. It's the x's are the ones that are going to become negative. Now, your ratios for sine don't use x's, they use y's over r's. And that's the reason as to why your ratios for sine in your second quadrant are remaining positive, okay? So, and again, that confirms what cast diagram says. In your second quadrant, the sine values are positive. Now let's reflect down onto the third and the fourth quadrant. Now, if we're reflecting about the x-axis, so in other words, we're going down, do you agree it's the y coordinates that are now also changing sign, okay? So because sine is the ratio of the y over the r, now you can see why these negatives are creeping in here, because obviously we're now working with the negative y over r, okay? That being said, the ratios of sine of 210 is a half. We're still following the same pattern of numbers as we're going through these special angles over here. The fourth quadrant, also sine is negative in the fourth quadrant because it's still your negative y values, and these will then give you your values for the ratios for sine in your fourth quadrant. Okay, so the first thing I want you to notice is there's a bit of a pattern going on here with these numbers, agreed? The only thing really that's different is that it depends on which quadrants we're in as to whether they're positive or whether they're negative. So let's take these points and let's now plot them on a graph. What we're going to do is we're going to make the vertical y-axis the value of the ratio, the sine ratio, and the horizontal axis is going to represent the angles, the degrees at the degree at which we're working at each of those angles. Okay. So, do you notice I've divided it into 4 colors over here? The first color, this blue over here, is representing all the points that were in quadrant 1, okay? Everything from 0 to 90. Then everything in quadrant 2, everything from 90 to 180 are your points in your second quadrant. There's your third quadrant, there's your fourth quadrant, okay? And you can see that what I've done is I've plotted, so at sine of 30 it was a half, so sine of 30 is a half, sine of 45 was root 2 over 2, sine of 60 was root 3 over 2, and sine of 90 was 1. So therefore, in quadrant 1, this is what the pattern would show us if I was looking at the ratios for sine. If I continued to plot each one of those values for your second, your third, and your fourth quadrants, look at what happens. Remember, they all were the same values on either side, right? Which means that you can see that this is how it's going to land up looking the same on the other side. And then remember, in quadrant 3, they became negative. So do you notice how all the y values are now becoming negative on your graph? And all the way back up to 360, which was back to 0 over there. Okay, so that is giving you your sine graph. That is what your sine graph looks like, okay? And there are a few pretty important things we need to know about a sine graph. The first one is this line over here. It's like a horizontal midpoint, okay? It's the halfway mark, the midline between the two halves of the graph, okay? Now, how many units above that midline and how many units below that midline was the maximum and the minimum point above and below the line? Well, you will see that, do you agree, in this case, the graph went 1 unit above the midline and it went 1 unit below the midline, all right? Now, that is what you call the amplitude, all right? The amplitude is how many units above, amplitude, how many units above and how many units below that midline does the graph go, okay? Now, the amplitude is always represented by the number that is in front of your sine equation, okay? Now, in this case, if you didn't see a number, obviously we know it's an invisible 1, and that represents the fact that it went 1 unit above and 1 unit below the midline. So the amplitude of this graph is what we refer to as 1, okay? Then the other thing is this. If I had this graph over here, so I went from 0 and I went all the way around the Cartesian plane and it kind of followed a path that went up and it came back down and then it went back up again and it got back to the starting point of 0. So therefore it followed a pattern. And then if I started from 0 again and I continued going around the Cartesian plane a second time, do you agree with me the pattern would simply continue? It would be periodic, okay? It would repeat itself, okay? If I did the following, if I didn't go in an anti-clockwise direction, but I went in a clockwise, now remember, in a clockwise direction is going in this direction around the Cartesian plane, and if you do that, remember the angles are always negative, okay? So that means that we have the option of a negative side of your graph as well, which would simply mean that everything would go in reverse, okay? So instead of going up to a half, it would go down to a half. And it would go down to root 2 over 2 at 45, and it would follow this pathway over here up to 180. So therefore, if we did the sine graph in reverse, no, it would then look like this. Okay, so the sine graph is periodic in nature, that it repeats its cycle every so many degrees. And do you agree with me that it is taking a total of 360 degrees to complete a full cycle of your sine graph, okay? So that represents what we refer to as the period, okay? The period is how many degrees is it taking for your sine graph to complete one full cycle of itself, okay? So the period of a sine graph is 360 degrees, okay? That's kind of your basic standard sine graph, all right? Now, I know that this might look a little intimidating, and there's a whole lot of points there to remember. So to make it a little bit simpler for ourselves, we kind of isolate the points of 0, 90, 180, 270 and then back to 360, okay? And because we know that this is the general shape of a sine graph, we don't need to put all of those points in between because it is a little bit time consuming. So if I were to sketch the graph of just y equals sine theta, okay, what you know about that equation so far is that the amplitude, which is how many units above and how many units below the midline is this graph going? Well, because there's a little invisible 1 over there, it means that it's going 1 unit above and 1 unit below, all right? Then the period of the graph, how many degrees is it going to take to complete one full repetition? Well, in this case, one full repetition is going to take a full 360 degrees, okay? So if we start with just the points of 0, 90, 180, 270, and 360, just to make our lives a little simpler, we know the following. I'm just going to do it with this. Sine of 0 we know was 0. Let's make that 1 and let's make this negative 1. All right. Sine of 90 went up to positive 1. Sine of 180 was at 0. Sine of 270 is at negative 1. And sine of 360 was back at 0. So your sine graph in its basic standard form is going to look like so. All right. That's what your sine graph looks like. Now we need to consider what happens if the amplitude or the period changes. And that's what we're going to deal with in the next graph, in the next video. So I will see you there. Well done.